Fine, or yeah, why don't you hold on to it for now in case we have questions? Yeah. Okay, so for those home, here's an online version for the 29th of March. Look at this piece of crap. I gotta get out of here. Honestly. Look at this. Look at this. You can't even hardly see me. Look at all this crap up here.
Even your home setup is better.
Oh, I don't know about that. If you saw the boxes you guys were sitting on, I was afraid you were gonna keel right over,
I still don't quite get why there's this piece on.
Oh, it's been there for years. It's a very good question.
Maybe they think that at some point we'll just fuse together.
Yeah, I hope so. I live for that day.
Well, you'll pass that one through there.
It's not bad.
Yeah.
Okay, so welcome, my folks. I'm so happy to be here, and I'm recording this for the folks at home as well. So, our goals are many. We'll take questions from you. Maybe we'll do the Clausur format first, so you know what's going on, and then we'll, with the remaining time, do a little on the rest of chapter 8, and that it will be it for the book. Question before we start, Noah?
Well, I have a question.
Let's keep that, but you know what? I just changed my mind. Let's do the Clausur format first so I don't forget.
Good morning, JFK.
In a moment.
One quick announcement to 7th and 8th grade band students that your rehearsal today, 9th period, has been canceled. That's it. Enjoy the sunny Tuesday.
So the Clausur Monday is periods 1 through 4. And here's how it'll go. You'll get given information as on the AP website, which is the same set of formulas and so on. I think I gave you a copy earlier in the year, but you can certainly look on the College Board website. Periodic table. Good. Part 1. Or let's call it part A. No calculator. And I'll do 50 multiple choice questions. I can't remember if they do 50 or 60 now, because it seems like they often put in extra ones as sort of trial questions or whatever, but I'm not going to do that. So we'll stick with 50 questions for that. And you'll have 90 minutes. Good. And you can use these, by the way, for both parts. sure folks at home can see this okay. Okay, then for part B. With the calculator. And it'll be more or less an FRQ test. Now, the modern format is 105 minutes. I'm going to have the clausura as 90 minutes, so I will cut that down for you to make it a 90-minute test. So we'll do 90 minutes for the first part, 90 minutes for the second part. And that's it. And they're worth 50% apiece. And as you can guess, they'll be mostly like the AP classroom quizzes we've had throughout the year, really. Okay, questions? No, I saw, and then Rhea.
So is this the way it's gonna be on the AP exam?
No, on the AP, I think it's 105 minutes for the second part now.
Okay, but so we have a calculator section with 50 or 60 questions. I mean, so,
Multiple choice is the first part for the actual AP exam also.
and we have no multiple choice section with a calculator.
Right. So there'll be no calculator for that part. Rhea.
I have two questions. For part B, so it's not going to be a full FRQ AP test because we have less time. right?
Exactly. So I will cut it down a bit because I want to make it doable within 90 minutes.
And the second one is for some other AP classes, we're doing like mock exams. So like we're doing the actual.
Yeah.
Like, are we going to do that for this class as well?
Yes.
Okay.
So, yeah, that's the scoop ski. Okay. Any other questions from you, Shilpa?
So what's the threshold for like the percentage you need to get a 5 of them?
I think I gave it to you at the beginning of the year. So it's the AP grading scale that we'll use for that. So, no.
When is the mock exam?
It'll be different days. What I'll do is for the time between our clausura and the actual AP at the beginning of May, we'll do a series of multiple choice tests and then we'll grade it. You know what I mean? And then FRQ test and grade it. And you can also look at, I'll have the scoring guide so you can see what the actual grader people use when they're looking at your FRQ part. Obviously not the multiple choice, that's just a straight scale. Yeah, so I hope you'll be well versed in AP stuff. And in the meantime, for a lot of days, also I'll try and continue to take questions from you. Please, I know you're feeling overwhelmed and I'm sorry this is the timing of it, and equally sorry I wasn't there yesterday with our crappy Wi-Fi. That wasn't my best class with you. But we'll just sort of hunker through. The good thing is you know most of the chemistry if you've gotten through chapter 6. Okay, chapter 7, you can more or less skim through, memorize the formula, look at how to use it. And by the formula, I mean this one.
So that won't be given.
That's really, it's given too.
Oh.
But I mean, you really know how to, you got to know how to use it. That's more or less chapter 8. Or chapter 7, right? Chapter 8 is a couple things. It's knowing how to do redox, reaction balancing, and finding voltages. Huge. Good. Anything else in both of those chapters is, it might be on the test, but it will be minor, so to speak. These are like the guts of each chapter in a nutshell, okay? Like I said, I know your time is limited. I understand that. No,
On are like is the AP grade gonna translate directly to what grade we'll have for the clausura? Because in
Yain, it's often close to what students get. However, you will have, once we take the clausura, more time to prepare as well. So your actual AP grade may be better than your clausura grade. Or if you do well in the clausura, it's really a good sign you're going to do well on the actual AP test.
I mean like because in AP calculus as our exam we're also going to take an AP test.
Yep.
But Mr. Welborn said that he usually gives everyone like one grade higher because we haven't quite fully prepared for the AP exam yet, and this is like the clausura.
Yeah.
How do you do it? Do you if
pretty
we
much
get,
don't do
over
that.
65%?
Yeah,
is that
so
a one?
I pretty much give you
Okay.
the grade based on our AP scale at the beginning of the year.
Mr. Welborn, he also is 100% is a 1. It's like that grading scale. I think, or like,
No.
at least the last coaches in real life, right?
No, but this one is an AP exam, full one.
So he's actually grading with 65%.
Yeah, but every, like, if you get a 4, he gives you a 5. Because of social.
Okay. Well, I'll bear that in mind, but I've always done it as a pretty much a straight scale. So I know the clausura is not easy. I also know you're a talented group, so I expect a lot of good grades because you've worked hard all year. And how should I say this? Be right with you, Tom. The AP test is not necessarily something you're going to cram for the last minute. Like you've been cramming for months with me, so to speak, cramming stuff in your head. And that's all going to pay off when you see this and you see the stuff that you've dealt with over and over and over with me. So, Tom.
I just wanted to do the order.
Yeah, of course. You may. And this video I'll have as well, Tom, so if you ever want to refer to it, if it doesn't crash, you know?
So for the actual AP exam, I think that, because we have the different units, I think 9 or so. But on the exam, are there some units that will be more on there than others?
Yeah. You can probably look this up somewhere online and see. Someone's done like for the FRQ parts, at least, this percentage of the stuff comes from equilibrium. This percentage of the stuff comes from periodic table trends. But I don't have that in my head. In general, there's a lot of stuff on equilibrium, acid bases, but other than that, there's also 5% of this, there's 10% of this. So I've not really given that to students because it also varies a little bit year to year. So I'm not sure how helpful it is with you. Other than the same ideas that we emphasize in class, like equilibrium and stuff, are emphasized on the AP test, of course, because it gets hit over and over in different chapters. Yeah, Maria.
In AP Calc, actually, we have this thing where there's specific types of problems that always come for the FRQs. And it's like from 6 different units, but those units then are always only like on the FRQ. Is there like a thing for AP Chem as well? Is it always like the same sort of units that are in the FRQ? Or like, does it really range from like everything?
Well, no, you're right. There's some that are like every year there's basically some sort of equilibrium problem on the FRQs. Every year there's usually some sort of acid-base problem. But having said that now, sometimes it's mixed with part A that might involve gases, or part F that might involve the Chatelet's principle, or you know what I'm saying? So it's hard to pigeonhole these and say this is a problem because they really tend to overlap a lot given that your knowledge now is capable of that this time of year. So, and Noah.
How many FRQ questions are we gonna have on the clausura with like ABC?
I'll probably cut off the last 1 or 2 short questions. That way it'll save you time.
So how many is it normally?
I think it's, 2 long and 5 short? I got to look it up and see. I don't have that in my head. So, but it will be an abbreviated version. And when you get the FRQ part, you want to read through more or less the whole thing and see what you got, and then plan your time. It's even worth taking a few minutes and do that. Read through, okay, this one I can do, this one I don't know. these little ones, okay, that looks possible. And you can do them in any order, you know? You just want to earn all the points you can possibly earn. So, and so on.
So we can't go back to the multiple choice questions after we've like turned it in and stuff.
That's right. You won't have any time anyway, but I mean, you once you're done with the multiple choice, you hand it in and that's it with that. Yeah. Okay, any other questions from you? Then I want to go to Noah because you have a question from the book.
Yes, on page 446, number 5.
446, 5. Let's turn to that and have a look, people and folks at home. So we're in chapter 7 with this one, and let's look at this. Chapter number 5 says we got a normal boiling point of water is 100 degrees. We know that. Its molar enthalpy of vaporization is 40.7 kilojoules per mole to vaporize the stuff. What's the change in entropy in the system? When 39.3 grams at 1 atmosphere condenses. Does the sign for the value make sense?
J per K, is that joules per Kelvin?
Did I screw something up?
The-
Kilojoules per mole on 1 atmosphere is your pressure, condenses, and it's the sign okay. Okay, not 0 Kelvin. So I appreciate your thinking in terms of temperature. That's nice. No, I won't do it. So I'm really tempted. Here, right. Okay. So if you haven't gotten this far, we're going to use a Sherry equation, which would be kind of handy for this. And it's this one. The delta S of the system equals, that's so weird. Because like the one we need is in the next section. I don't know why she does that. Is delta H over 2. And I truly hope this is what's going on. Okay, so first off, so we got some steam and it's becoming water. And it's condensing. What's happening to the amount of disorder if it becomes a liquid? What would you think? Lena?
I would say it decreases because
You got it. It decreases. So if it's getting more ordered, what should be the sign on my delta S? When?
Negative.
I think it's negative in this case because we're getting less disorder. So let's see if it comes out that way. I hope. Okay, here we go. So as this stuff vaporizes, I got to put this in. So as it's condensing, Oh, it's condensing. What do I gotta do with the sign of this sucker? If it's vaporizing, I gotta do what? Put the energy in to vaporize it. So if it's condensing, I've got to Shilpa make it negative. So I'm gonna write condensing just to cheat. So now it's gonna be negative. And we're gonna get that negative that Quinn alluded to earlier. So look at our equation, delta H. Well, what's the change in heat? Is it this much? No, because we didn't have a whole mole. We'll have to just do what? We got to change our grams, folks, to moles. And we can do that in the problem. Let's do that to save time. So delta S of the system is 39.3 grams times molar mass of water, everybody? 18. Yeah. Times, and with Shilpa's help, we got the right sign on it now, so it's 40.7 kilojoules per mole. And you know what? I'm guessing we're gonna have to change it to regular joules, because I think delta S is in joules.
Yes, ask for in joules per
Does it say that?
Kelvin.
All right, super. So then we'll have to go what? 1 kilojoule, everybody has 1,000. Right? I think that'll work. Multiply by 1,000, makes sense? Okay, then we gotta divide that sucker by the temperature in Kelvin, and I assume it's standard temperature. Oh, well, it's not actually. This is happening at what temperature?
373 Kelvin.
Oh, because that's the temperature, right? 100 is the temperature it's boiling. So 373, however many zeros they put on that. Kelvin, beautiful. I think that will give you, Noah, the right answer. Let's find out in question from you.
So the top part is finding the delta H
Exactly.
using this information. Is there a form? I assume there's a formula, but I forgot. And I get the formula
For
to
what?
find delta H.
No, there's not really a formula. Remember, delta H, Noah, is the change in heat. And I can have it two ways. I can have the delta H as a nice number if it's the molar change, so per mole of stuff. But if it's not per mole, then all you got to really do, Noah, is get a fraction of it. So how much of this? Well, the fraction 39.3 over 18, because it's more than a mole. You know what I mean? So it's just a fraction of this amount per mole, because I got a couple moles or whatever here that is in, that's condensing. That's all I'm doing. So I'm doing it just for this situation. Good question, though. Other questions from all of you?
Does like it asks then, does the sign for the value you calculate make sense?
Yeah, and I did that question kind of first off with Quinn, and really the rest of you too, with Lena as well. So it's disorder is decreasing, and therefore it's going to be negative. And I got a -1 up here, so it better come out to be negative something. And so yes, it should be decreasing because it's less ordered. No, it's more ordered, less disordered. Less disordered. Okay, I hope that'll work for you. I think that's how to do it, Noah. Questions from you or anybody else? Other questions on any of the chapters? It doesn't have to be chapter 7. We can go back as far as you need. I know you're all in different places, and I understand that. No, go ahead.
I have a question from chapter 6.
Sure.
Page 434, number 1.
434.1. Okay.
So the question says for each of the 3 oxides and water that result in the production of the acids responsible for acid precipitation. But in the answer key, they take SO2, and I forget what they add it to, but they don't add it to water. I was just confused about that because the question clearly states that we're supposed to take 3 oxides, NO2, SO2, and SO3, and water, and then like.
And they don't do it for one of them.
Well, they do SO2 plus I don't know what. I can try to find it, but it something
Okay,
else.
well, to help everybody, let's list off what you know already and what you've said. The question is, we're writing the formulas for the reactions between the oxides and water that make acid rain. Okay, so list me the two that you got, Noah, that do have water in them.
So NO2 plus H2O, well, 2 NO2 plus H2O react to form HNO3 and H2O. And then I
And
had
what was the last chemical?
HNO2
HNO2.
and SO3 plus H2O react to form H2SO.
H2SO4.
Yeah,
Okay. I wouldn't have normally done that one, but if that's what they want. Usually I do this one. Another byproduct is sulfur dioxide. That's what comes out of a lot of chemical plants. And you get an acid which is icky, but it's not as icky. And what are Quinn, you probably know, what are the names of the two of them?
well, that's the last one. SO2 is
Oh, that's the last one.
yeah.
Oh,
And except in the answer key, they don't mix it with what I'm trying to find what they mix it with.
they don't mix it with water?
Yeah.
What do they got against water? I've always learned it this way, where this one is sulfuric and the next one is sulfurous. And that one's less, that's a weak acid. And that's often the one that develops in like acid rain lakes and stuff,
Yeah,
okay?
they mix it with just oxygen gas, O2. They do
And what do they get?
when they get 2SO3. They do 2SO2 plus O2 react to form 2SO3. It just confused me because it clearly stated in the problem that you're supposed to mix it with water, and then they don't.
Okay, so Cheryl's playing the game. Let's see if they know that to get SO3, I can also start with SO2. So don't lose a lot of sleep over it, Noah, but I think all she's doing is saying, okay, I can build SO3 by adding SO2 plus an O2 up here and make that. So, but as far as I know, I can also get sulfurous acid. That's the way I learned it, by adding water to that and getting sulfurous, H2SO3 instead of H2SO4. Either way, it's not very good for the fish, whichever ones you got there. Shilpa.
Just a general question, when do you know when to use the double arrow and the single arrow?
Oh, I don't know.
Does it not matter or?
If it's an equilibrium problem, you definitely want to use both. I don't know. I would say you could use both here too. It doesn't really matter, as you probably have guessed by now at this point of the year. Good. All right. So no, rest your mind easy on that. And to be honest, there's one other one that we can put in here. You ready? What about CO2? I'll do double arrows here for grins. And what would be the acid I would get? Can you throw it together and kind of build it? What do you think, Shilpa?
H2CO3.
Yeah. Well, that's an acid too, except you might know something about this acid. Well, first off, where do we find that acid? No?
In like is coenzyme.
It's colloidal, right? It's in fizzy drinks, right? Carbonated beverage. And so it's unstable. So you're probably not going to find a lot of that acid in lakes because it tends to bubble out as CO2, especially if it's warm water. Okay, that's more or less just for grins, all right? Okay, does that help, Noah?
Yeah.
Okay, all right, good. Other questions from anybody else, any chapter? I don't have my phone, so I can't tell if anybody's got a question from home. Lena?
Chapter 6, page 392. Number 3.
Good. So 392, number 3, we got a student is doing a titration, and we got 25 milliliters of acid, of acetic acid, And do I have a reasonable piece of chalk? No, no one ever. How come I'm the only one that replaces the chalk? This drives me crazy. Look at, I got yellow. Do you mind yellow chalk? Is that all right? Do I mind yellow chalk? Obviously I do. So be it. It's a yellow day. I'm sorry, where were we? Okay, and the concentration is known to be approximately 0.2 molar. So 1 sig fig, not very accurate. After adding a small amount of phenolphthalein, love that. Don't you wake up at night saying that word just because it's so much fun to say? Sorry. The student fills a 50 milliliter burette with a standardized 0.0650 sodium hydroxide. The standard means that's what they're using to titrate this stuff, and begins to titrate. His lab partner insists that the titration cannot succeed. Do you agree or disagree with the lab partner? Okay, look at the numbers and you tell me why this sucker is not going to work. No.
I don't really understand why, but I believe it was something to do with the large difference in the molarities of the two. Like one is 0.2, which is, well, compared to 0.0650, relatively big, large molarity. And I think that's the reason, but I didn't understand it.
Yeah, you're really on the right track. Right track. Let's add to that. No D.
I would have just said something similar that because it's 25 milliliters of acetic acid compared to the 50 milliliters of NaOH. Like there's not going to be enough NaOH to compete with the 0.2 molars of acetic acid.
Okay. Remember, yes, exactly, Noah. Remember, everybody, you're trying to reach the point. What's that one called? The magic spot, Tom? Close. It starts with EQ. Equivalence point. There you go. So at the equivalence point, that's when you actually have the titration complete. You got what? The moles of acid equals moles. Sorry, I'm writing poorly. Equals moles of base. So the easiest way I would do this is with numbers. You ready? We know all the data for which thing, the base or the acid side. What do we know our data for? Tom.
That's if you fail every last arrow, so the NaOH, right?
Well, we know all of the data though that we need
Oh, wait, sorry.
for the acid or the base side. I don't care about the phenolphthalein because that only is a color changer for the acetic acid. So let's do the acid side. Ready? Remember this equation? The one Cheryl doesn't like?
Mv equals Mv.
Okay. So it's molar concentration times the volume, and A stands for the acid, please, and B for the base. Okay. And it's based on this idea, isn't it? The moles of acid equals the moles of base at the equivalence point. So chuck in the numbers. You ready? Here we go. We got 0.2 molar times 25 milliliters equals, well, we got 0.0650 molar times the volume of base. Crank it out, people. What's the problem? Gwen?
You're gonna need more sodium hydroxide.
Yeah, because my burette's only 50 milliliters. Somebody give me a number. How many milliliters, Shilpa?
I got
77.
76.9.
Okay, 76.9 milliliters equals the volume of base. So a 50.00 milliliter burette, as Quinn alluded to, is not going to work. Is not enough, or has not enough base. It's a basic problem, isn't it? Sorry.
But can't you also argue that because they give you approximately 0.2 molars, that could be like 1.6, in which case, it might actually, the titration might actually succeed.
Did you do it with 1.6? Is it
I
less than 50? Because I'm guessing Sherry's pretty clever. Even at 1.6, I'll bet you anything, it'll still be more than 50. Crank it out and see. I think you're up Basic Creek here. I think you have a problem. Well, be that as it may, my point with doing this is you can argue, but you may also want to just do the numbers and show that it doesn't work.
Okay, yeah, it's.
It also is more than 50?
Yeah.
Okay, so won't work. That's why I put that one in there, to get you thinking. That's why I gave you that problem. Good. Any other problems in any chapters we'd like to look at? You're asking about good ones. Ones to learn something from. No. I'll let you be thinking. In the meantime, I'll go to where I need to go with you. Okay, so if not, I want to do a little more on section 8.4, which is critical for your understanding how to do this sort of thing. And let's look at page 516. So what I want to do is see that battery at the bottom of page 516. Actually, I like it better on 517. It's almost the same, but they added something that makes it nicer. They added the ions that are in the solutions. So let's look at that. At the bottom of page 517, we got a magnesium stick sticking in magnesium nitrate solution and a copper stick sitting in copper nitrate. And then we got this weird thing. Did I show you a salt bridge yet? Did I physically show you one yet? Let me go get one. Just so you know what the scoop screw is, okay? I can't put my hands on a good one, but that's at least adequate. Okay, so the salt bridge is full of, surprise, salt. In fact, this one, if you look at it, what salt's in that sucker? NH4NO3. So ammonium nitrate. And what that does is it's got here at the ends, it's got some little places that the stuff can come out. It's a semi-permeable membrane, so some ions can go through this. And the reason you got to do this and have this thing in there is you got to keep it sort of electrically stable. Tom, you with me? Okay. You got to keep it electrically stable. In other words, when we start having ions that become solid, you're probably not understanding what I'm saying. Let me write this. Let's be a better teacher. So, still on this page, I'm going to sketch this. And then we're going to get back into voltage. I know some of you are not even started all of this yet. It's okay. I'll lead you through, but keep your brains on, all right? Okay, so here's what we got. Here's my salt bridge. Whoa. Let's just change color. Here's my Mg. Here's my Cu. Here's a little thing. Here's a voltmeter. And I assume that's going over here.
Stick of Mg purposely larger than the sticker.
No, although it doesn't matter, actually. The size doesn't matter. It's just got to be present or not. Remember how solids don't matter in equilibrium? Same thing here. So it's either present or it's not. Okay, so liquid level. Oh, really looking 3D. Amazing. So we got some Mg2 pluses here. We got some NO3 minuses. And here we got some Cu pluses, or what they put in? No, 2 pluses. So copper 2 nitrate, NO3 minuses. And here we got, as Shilpa said, NH4 plus, and again, some nitrates floating around in there. All right, this is actually a really good one to talk about, but we'll cover 8.4 doing this as well. Okay. The really stupid but useful rule that I have given you is to see what's going on. Go to the redox half reactions on page 569. So turn to that. And you're looking for one that is on the left side, an ingredient that's high, and on the right side, an ingredient that's low. And if it sounds like I'm just asking you to remember a rule without thinking, you're right. And I almost never do that with students. However, the logic will come later. For now, left high, right low. Okay, so find the reactions. What do we got? We probably got something that involves Mg and something that involves Cu, right? So find them both and call out the voltage number just so we can find it.
0.52 for Cu plus E minus.
0.52?
Yeah.
Super. Now, problem is it's Cu plus. We need Cu2 plus.
That's 0.15.
0.15.
2 rows below.
Now, that's going to Cu plus, 2 plus to Cu plus. That ain't going to work. We got only Cu solid. We need like both ingredients. So it's got to be Cu2 plus and Cu solid. Shilpa?
Well, for now, I found magnesium. Should
Okay, we'll come back to that. Do we have one for Cu2 plus going to Cu solid?
Yeah, that's 0.34.
All right, everybody put your finger on that. We need that one because that's what we got. We got solid copper and we got Cu2 plus. You know what I'm saying? Okay, now keep your finger there. Shilpa, where's the other one?
-2.37.
All right, negative 2 point or 0.2?
2 point.
Oh, it's way down there. Okay, so how is this thing going to work? What's my ingredient that's on the left side that's higher and on the right side something that's lower? Yeah, Shilpa?
Oh, sorry. I'm not sure.
Okay, look at those two reactions. Which one, what chemical is on the left side that's higher? And on the right side, there's one that's lower. I know it's a weird question. Lena,
Cu2 plus on the left side that's higher.
good, stop. Write it down. Good, and continue now, Lena.
And Mg solid that's on the bottom right.
Super. Watch what I do. I'm putting them together now. Now, here's what that means. I'm going to take the two reactions. Where I'm going to cheat and kind of put it like this, but I'm going to put the two reactions up above. Cu2 plus 2 electrons forms Cu. And the other one, because it's on the right side, I got to write it backwards. And there's the thing you need to know. The one that's lower down on the right side, it's got a negative voltage in this case, but whatever it is, you've got to flip it around. So it's going to be Mg solid going to Mg2 plus 2 electrons. Before you run off, let's get the voltages again. The regular one, the Cu was 0.34, was it that one?
Yeah.
And the other one was what? No B?
It was negative 2.37, so now it's 2.67.
Now positive. Good. We'll continue there after break. But I want to get that far, especially for folks at home. Goodbye. See you in a little bit. I'll lock the door.
I have class now, but I still had a question. In the video, when we multiply, but here we don't have to, but if say we have one electron or
Yeah.
something, we don't have to multiply the voltage?
No, that's the cool thing because they only are representing, Noah, how much energy is dropping for electrons of that sort in that reaction. It's not about the number of electrons, it's about what the drop is in energy. It might have 10 electrons going here or 50, it doesn't matter. It's the same drop in energy.
Okay, so why do we have to reverse the sign then?
Well, because instead of from going to, if I have it this way, it gives off energy, positive.
Oh, okay.
If I have it the other way, I got to put in energy to make it happen.
Okay.
Okay, let's end it